entropy, and to be more specific, we'll talk about increase in entropy. Okay, and then we went on to define what is entropy. So to define entropy, we looked into Carnot's theorem, its corollary. We proved that for a given TH and TL, the reversible engine will be more efficient. Okay, so we looked into this proof. Any questions or doubt? Please feel free to stop and ask. Okay, so we assumed something and then we found the contrary, and then we ended up with this result that the reversible engine has more efficiency than irreversible. So we also talked about the Clausius inequality, that dq by t will be less than or equal to 0 for all processes, for all engines. Then we talked about entropy. We said that entropy is a property of the system. It is a property like volume, pressure, or temperature, and it is a point function. It is not path dependent. So we discussed, so I have added some more clarifications here. So you can see that dq by t for a reversible process will be ds. Okay, if it is irreversible, it will be less than or equal to ds. So I think till here we have discussed, right? So we have seen that ds of universe is always greater than or equal to 0. It means that entropy of the universe is always increasing. Okay. So we can summarize that entropy of an isolated system during a process always increases, or in the limited case of reversal process, it remains constant. Okay, last class there was a question on what is the maximum limit or how till when it is reaching. Who asked? Is that student present today?
Yes, sir.
Okay, so one more, I thought about it, one more limiting case could be that, see, theoretically we say that it will, entropy of the universe keeps on increasing, but theoretically a maximum could be achieved if all the matter in the universe is at equilibrium with each other. Everything is at the same temperature. There is no unbalanced force or any unbalanced any sort of, everything is under equilibrium. That could be a case where entropy will be maximum. Then after that it will not change. Okay, so that is the basic idea. Are you clear now?
Yes, sir. Like we can think like all the matters will means break down to hydrogen or helium. Like
Yeah, it is much beyond the scope of this course, but you can imagine that, see, when there is an imbalance, the natural tendency is to create balance. For example, if you have two bodies at different temperatures, you connect them, heat will flow from hot to cold. Okay, so when they are in equilibrium, when they come to the same temperature, then there is no heat transfer.
yes,
Okay,
sir.
that is something we need to achieve. That is how the entropy will be at stabilized. So basically, we'll whatever the processes we'll consider, we'll see that entropy is increasing. So let us limit ourselves to that. But yeah, theoretically, it is an interesting thought, and I will suggest you read that Stephen Hawking's book, Brief History of
Yeah,
Time.
sure. Yes,
It
sir. I
actually
will.
says that you cannot, so basically it gives so much importance to entropy that he says that universe is expanding and time, so basically if you want to make a time machine, you want to go back in time. Okay, so the only logic he has given is you cannot go back in time because it will violate the second law. Entropy will decrease if you go back in time. So just imagine, this is how entropy is important. Okay, so anyway, we will not will limit us to this premise now, and if you want to discuss further, we can take it off the class. Okay, so this is what
Yes,
we stopped at in the last class. We summarized two statements by Clausius where he talked about first and the second law. Okay, so let us. So this is what we stopped at yesterday, last class. So any questions still here, or should we move forward?
So move forward.
Okay, so let us talk about entropy and equilibrium. Okay, let us say that we have a chemical equilibrium. Okay, so I want to make it clear that we will not be studying any chemical reaction for this course. I have taken just for an example, just a sample case for example. So let us say that we have a chemical equilibrium between four species A, B, C, D. So let us say A at the stable equilibrium. Okay, when the things are not changing, the forward reaction is equal to backward, then only you will get a stable equilibrium. So at that case, let us say we have 100 moles of A, 100 moles of B, and 100 moles of all the species. So when we have 100 moles of all the species, we have a stable equilibrium. Okay. Now let us say we have started with A and B. Let us say we started with 99 moles of A and B, and initially we have 1 mole of C and D. That is the initial reaction. We started with that. And let us say we can also start from this C and D. So we can start with C and D being 99 moles. Okay, or let us say 99%, and A and B 1 mole each. So these are the two extremes. We can start from here, but finally the stable equilibrium is at this concentration, 100 mole for each product. Is this clear to everyone what I am talking about?
Yes, sir.
So what I am saying is that we can start from here or we can start from here. We will end up here because this is where the stable equilibrium is. This is the state of stable equilibrium. Okay, now what will happen? If I start from here and the reaction, so this is reaction progress. So the reaction goes in this direction. Reaction will try to move towards this. Okay. So entropy, let us say start from here. Entropy should increase or decrease while going this side. While approaching this, entropy should increase or decrease.
Increase.
Okay. Let us say entropy increases. What about here? I start from this. Now, this is not stable, this is stable. So entropy will, if I move from here to entropy will increase or decrease?
Increase.
Increase
Again,
only.
so entropy is increasing. So if I move from here, entropy is increasing. I move from the opposite side, entropy is still increasing. So where it will stop? It will stop at the stable equilibrium.
Equilibrium.
Okay. So at equilibrium, let me draw it more clearly. So at equilibrium, what we'll see is that entropy has become, entropy is not changing at all. Okay. So we have a point where the slope is zero. This is your maxima and this is your equilibrium position. Okay. So basically at your equilibrium, you get ds by dx, x could be any variable. So this is your maxima where you get ds by dx equal to 0. Okay, so this is how entropy controls equilibrium, or that is why, because that is why the equilibrium is stable. Okay, because entropy is maximum here. Now let us say I want to shift this side. It is a reaction or any process I want to shift. So entropy will decrease. So the system will tend to go back. Okay. Similarly, if I want to go in other direction, it will go like this. Entropy will decrease. So the system will again try to shift back and it will again fall to the stable equilibrium position. Okay, you can imagine that it is like a valley and it represents some hill or some valley. Now if you have a ball here, okay, so the ball is now in stable equilibrium. If you want to lift it up and leave it here, it will fall back. If you want to lift and keep it here, it will fall back. Similarly, for any process under equilibrium, if you remove it from a stable equilibrium place, it will come back to equilibrium, because if you go to other sites, entropy is increasing, entropy is decreasing. Is this clear?
Sir, I had a one doubt over here. Like,
Yes.
sir, if we say that the universe entropy is increasing day by day, but sir, as we see the solar system and Earth, Sun, Mars, Earth, Sun system, then they are coming at the same position after a point of time. So why are we saying that the entropy of the universe is increasing day by day? And as the graph suggests, that if something is going up in the equilibrium, it will come down as well at some other point of time.
No, no, I am saying that it is not going up. We are taking it. So this is a stable equilibrium position. Okay. If we remove it from that, it will try to restore. Naturally, it will not go away from equilibrium. The natural tendency is to stay here.
Okay, sir. So,
Okay.
but
So
if
this is let me finish. So this is for a system under equilibrium. Okay, universe is not a system which is under equilibrium. Universe is always expanding. Okay.
okay, sir.
So don't confuse universe from here. So we'll talk about at the end of this slides. We'll talk about probability and microstates. So then I hope it will be more clear. But okay, let us take your example. So sun and moon, sun, you say sun and planets are coming back to the same location. Is that what you meant?
Yes, sir.
Yes. Okay. So actually, this is beyond the scope of this course, but let us talk about geography or astronomy. So Sun is also making round of Milky Way. Are you aware of that? The,
No,
po-
sir.
Yes, sir.
the position of Sun is not fixed. It is also moving along with the Milky Way, and all the galaxies are expanding. Okay. So the position of no body is fixed in this universe. Everything is expanding. We are occupying more space, and it is, of course, becoming more disorderly. Okay.
Okay,
So, for
sir.
example, let us say that we have. So, I'm just making a very simple example for you. So, let us say we have two gases in different partitions. If I open, they will mix. So the natural tendency is that entropy will increase naturally. Okay, we'll talk about this in later slides. So last slides we'll talk about what entropy means, or how you can interpret entropy for microscopic scale. I think that you can extrapolate for sun or stars, but I think it will be more clear when we go to that. Let us finish some equations, then we'll talk more about that. Fine? Is it clear?
Yes, sir.
Okay, so we have some derivations to make. So first, let us do that. Then we'll talk about some theoretical ideas on entropy. So at equilibrium, we say that, let me delete all this. So at equilibrium, we say that entropy is maximum, or ds by dx is equal to 0. Now this x could be anything. It could be your reaction progress or temperature. Whatever the variable is, entropy is not changing with that variable. That is the idea. Okay. Now, let me delete this first. So what we understand is that under stable equilibrium, okay, the entropy of the system cannot decrease because it is already at the maximum. Right? Now it cannot go away from that state because it will decrease the entropy. So the system naturally will try to remain at this state, and this is what we call stable equilibrium, where your entropy is maximum. Okay, is this clear?
Yes, sir.
Okay, moving on. So we'll talk about how we apply entropy for some simple examples. Okay. So do you remember this slide we talked about in the second law? It
Yes, sir.
is flowing from hot body to cold body and not the other way around. Okay. So in that chapter, when we talked about the second law, we just talked theoretically. We have given statements. Okay, but if suppose someone asks you to prove mathematically, give me one equation which can prove that heat flows from hot to cold or not the other way around. Can you give any equation to prove that? Okay, so we'll look at the equation now. So after 2 slides, you will have mathematical proof that why heat travels from hot to cold and not the other way around. Okay, let us look at that. So let us take some simple example. Let us say that I have two. Let me get a pen. So let us say I have two objects A and B. Okay, let us say that there are temperatures TA and TB. Okay, and what do you want to keep higher? Let us say TA is higher than TB. So A is hotter than B. Now if I connect, let us say we connect it using a metal pipe or something which has negligible mass. So we'll not talk about any changes in this pipe. We'll talk about how things are changing with A and B. Okay. So let us say we connect A and B and there is some heat lost by A. Let us say Q amount of heat is lost by A and that heat is gained by B. Okay. So what is the heat gained by B? Q. We'll assume that the system is insulated. Let us say that this is insulated like this. So there is no loss to the ambient environment. Is this clear to everyone?
Yes, sir.
Yes, sir.
So two bodies are there, we connect it and we insulate the whole system. So no exchange of heat with the surrounding. Heat is getting transferred from A to B. Now let us talk about entropy. What happens to entropy? So entropy of this whole system will be A plus B. I said that this is a tube. We'll neglect everything about the tube. Let us say it is an ideal, massless, any nothing is there in the tube. So it is just connecting A and B. Okay. Now, system entropy is sum of entropy of A and B. Okay. Now, same for the universe because we're not exchanging anything with the surrounding. We'll say that universe. Okay. So generally, when we say universe in this subject, we mean system and surrounding. Okay. For calculating entropy of A, you will not take into account some volcano at Jupiter. So universe means that whatever is surrounding that. We generally limit ourselves to the room, to your room, to your house, that's it. Universe is a very big term, but we use it for just the near surrounding. Okay. So for delta S of universe, we'll say that what is the change in A and B because we are assuming no heat exchange with the surrounding. Can I write like this? Delta S of A as minus Q by TA and delta S of B as plus Q by TB. Is this okay to write?
Yes, sir.
Yes, sir.
So why is this minus and this plus?
So because one is losing the heat and one is gaining.
Correct. So because that sign convention that we have defined, we say that somebody is losing heat, it means it is minus Q. If something is gaining heat, it is plus Q. Okay. So
Sir,
now
why are TA and TB constant here also? Are these also reservoirs?
no, it is not reservoir, but okay, let us say we are taking small amount of heat such that this temperature is not changing. We'll talk about a case where the temperature changes. In the next example, the temperature will change. To keep it simple, let us assume that temperature is not changing, or there is a very small change which is not appreciable. Fine.
Okay.
We can say that Q is very small. That's a good question. Okay. So if I solve this, I will get something like this. Fine. So you can just substitute and you will get deltas of universe is this expression. Now what is this? This is proportional to TA minus TB, right? Now
Yes, sir.
if TA is more than TB, that is what we initially assumed, then delta S of universe will be more than 0. So heat transfer from a hot body to a cold body increases the entropy of the universe, and hence it is spontaneous or natural. Okay, so this is the equation that we have. Now, if you are given two bodies, if you don't know which is hot, which is cold, you can simply assume something and then you calculate delta S and see whether this is positive or negative. So naturally, for all natural or spontaneous processes, this has to be more than or equal to 0. So based on that, you can determine which is more, TA is more or TB is more. Is it clear?
Yes, sir. Yes, sir.
So this is the equation. You can try it. For example, if you talk about tea or ice cream, you can substitute their temperatures. You will see that for a tea, this temperature of tea is more than atmosphere. Okay. So let us go back to that slide. So here we know that temperature of, let us say, T is T1, ambient atmosphere is T0. This quantity is positive. So entropy will increase if T loses heat. Okay, similarly, if I say this is T2, T2 minus T0, it is positive or negative?
Sir, negative.
Negative, because atmosphere is at a higher temperature.
Negative.
So that's why it receives heat. If it loses heat, then it becomes a negative, entropy will decrease. That is not going to happen. So this will receive heat. Okay,
Yes, sir.
fine. Now let us go back to another example. Let us say that we have, okay, now we'll see the change in temperature. Okay, the last example was to keep it simple. Now let us make a little bit complicated. So let us say there are two fluids. It could be liquid or gas or anything. Two fluids A and B with M1, C1, T1. This is for A, mass, heat capacity and temperature, and M2, C2, T2 for B, where T1 is more than T2. Okay, now let us say that I open this partition in between. So what will happen? The fluid will mix. And let us say at the end of the process, I have a mixture of A plus B, which has a mass of M1 plus M2. Temperature is reached TF. So TF will be something between T1 and T2. Okay. So this is the final condition. Now let us talk about what happens to entropy of these fluids. So how much will be the heat lost by A? A was initially at T1. Now it is reached to final temperature of TF. Okay. So some heat is lost by A. We can write M1C1 into T1 minus TF. This is the delta T. MC delta T is the heat lost, right? Now, what will be the heat gained by B? B sees a change in temperature. So B is initially at T2, now it is finally at TF. So it gains some amount of heat. TF minus T2 is what B gains. Okay, now these two should be equal. How much A has lost, the same amount of heat has gone to B, right? Let us say again that this whole system is isolated or this is insulated. So no heat exchange with the surrounding environment. Fine. So for that assumption, we can say that heat lost by A is equal to heat gained by B. Is this clear?
Yes,
Yes,
sir.
sir.
Now from this, can I calculate TF? Okay, so if you do some algebraic manipulation, you will get TF in this term. Okay, now what about entropy? So how will I write entropy change of A? See, it is again mixing, the A is mixing and it is forming a mixture, but still we can say that, let us say there are some distinct molecules of A and B. So we are talking about those molecules. We say that they are losing some heat, so they will be changing entropy. So what that will be? Delta S will be dq reversible by T. Okay, so dq is basically your mc dt by T, which will be equal to, mc is anyway constant, so I've taken out of integration. So this will be log of Tf by T1. Is this clear to everyone?
Yes, sir.
So why you have
Yes,
written DQ reversible?
Okay, good question. So this, when I say delta S is equal to, it has to be reversible process. It is actually not a reversible process, but as we have discussed that delta S will be same for reversible and irreversible. Sorry. So what we have discussed is that if you go from one point to second point, the delta S will be the same whether you go by irreversible or reversible. Okay, so we'll talk about entropy generation also. Just wait for a few slides. But here I want to calculate delta S. This process is irreversible. So how do I do? I cannot calculate, I cannot use this equation. So I take another path which is reversible and I integrate along that path.
sir. As one thing more, sir, as it is a point function entropy,
Yes,
so why can't we write it as S2 minus S1 directly?
we can write, but how will you find S1, S2?
Sir, Q by T as directly
Uh,
Q1 at point.
See, it is
No, we
actually,
can't define any enthalpy at any point. We just can define change.
yes, we will come to that. So absolute entropy is basically defined with respect to 0 Kelvin. Okay, so just wait for some more slides. At the end of this, maybe tomorrow we'll talk about absolute entropy. Okay, right now we cannot define as simply, see, you see Q by T, right? Is what you're saying.
Yes, sir.
So
So
how can we define Q at a point? Q
that is the problem. You cannot define. That is what I am coming to. Q we cannot define. So generally, what definition we give is that entropy, we assume that entropy at 0 Kelvin for a perfect crystal is 0. So then you can define Q, that for the present state how much Q has to supply. But that is a different concept. So let us talk about here. So it is not. So you will have actually you have tables also which give S1 and S2, but the tables are calculated using these equations. So let us focus on this. So S1 and S2, it is not straightforward to define. So we take these equations. I hope this is clear, or you still are
Yes, sir.
fine. So let us go by this. We'll see why or how to define absolute entropy. Okay. So now let us come back to A and B. So entropy change for A, we have found this. Okay. Now entropy change for B. Sorry, this will be for B. It will be again for. We correct it. So entropy change for B will be same. Let us say they have T1 and T2. So again it will be MC delta T log of TF by T2. Okay, now tell me which one is positive and which one is negative. Will it be positive or negative?
so S1 is negative. That I
S1
One is
negative and S2
negative.
positive.
This one is positive because it is getting heated, it is losing heat, and you can also look in this equation that TF is less than T1. So this log will be negative and this becomes negative. Similarly, TF is more than T2, so log is positive and this whole term is positive. Fine. Now, what is the total change of entropy in the universe because of this mixing? So that will be the sum of S1 and S2. Again, I am assuming that no heat exchange with the surrounding. So S1 and S2, delta S1 and delta S2, we have seen these values in the last slide. Now I'll simply add that. So for mixing of two fluids, we have delta S of universe is the sum of MC log TF by T1 plus this. This is the delta S of mixing. So based on that, you can calculate TF. We'll see how. So let us take a simple example. Let us say that we have two fluids where mass is the same and let us say C is also same. So let's just write C. Okay. Now using this equation, we can, if we substitute these values in this equation, we'll get that delta S of universe is MC log TF square divided by T1 into T2. Okay. So I am leaving this as a homework. You can substitute these values in this equation and try to obtain this. Okay. If you don't get, let me know, but it should be straightforward. Okay, I want you to give it a try. Moreover,
So we will get that.
yes, I know, that's what I'm telling you. Moreover, you will also have TF will be an average of T1 and T2 because mass is same and C is same, so it will just the arithmetic average. Okay. And when you substitute TF in this equation, you will get this. Okay. So this 2 will become, square will become 2 log, which will go like this, and this will become root of, just try it out, substitute and see whether you are getting this or not. For equal mass and equal heat capacity, specific heat, you should get this. Okay, so just try to derive and see whether you're getting this or not. I'm leaving this as homework. This is a simple result for a simplified case. Okay, so based on this, for example, if you are given some values for mass and C, you can calculate what is delta S or what is TF. Even if it is not equal, you can substitute and calculate using this equation. Okay, moving on. Now let us talk about different processes that exhibit external mechanical irreversibility. You don't have any class, right? Can I take 5-10 minutes more?
Yes, sir.
Yes.
Okay, so let us try to wind this up. So external mechanical irreversibility. Now, isothermal dissipation of work. Okay, so let us say I have an electric heater, room heater. So I supply some current I is flowing through it. It will generate heat, right? And let us
Yes,
say
sir.
that we consider electric current, we take it as electric work. So let us say this W dot is the work that is supplied to the system and some heat is generated. Okay. So for steady state, we'll say that, or for any state, the rate of work done or rate of the electric work supplied will be equal to the rate of heat generated. The same work is getting converted to heat, right? Now,
Yes, sir.
what is the change of rate of change of entropy of the surrounding? So surrounding, let us say ambient air is at the temperature T. Okay, now it is receiving heat. This is the rate of heat. Dot is rate. So it is receiving Q dot at temperature T. So the delta S is Q dot by T. Fine. It will be equal to W dot by T because W is equal to Q. Now what is the, how can I say that delta S of system is 0? In what condition?
Isothermal.
Isothermal, or I can say it is steady state. Okay, so the system has attained equilibrium and the temperature of the system is not changing. Whatever heat, whatever work input it is giving, the same amount it is losing as heat. heat is being dissipated to the ambient. So the system, there is no heat supplied here. Okay, Q is equal to 0. Q is not coming, but whatever work is coming is getting supplied to Q. Right? So delta S of system is 0 for steady state. So I can write delta S of universe as this, which is equal to W by T. Is this clear to everyone?
So can you explain delta system is zero?
Sorry, your voice is breaking. Can you please repeat your question?
So can you please explain why delta S system is equal to zero?
Okay. So for the system, the system temperature, when I assume steady state, I say that, where is this? Okay. When I assume steady state, I assume that the state of the system is not changing. It is at constant temperature. Okay. There's no heat being supplied to the system. System is getting work input and work does not give any change in entropy. Okay, this is an important point. Work, whether you supply work or whether the system is doing work, there is no change in entropy of the system. Okay, so work is not changing in entropy, and that work itself is getting lost to heat, to the surrounding, not to the system, to the surrounding. So whatever changes are there that are being done to the surrounding and not to the system. So for a steady state, I can very safely say that delta S rate of change of system is 0.
Okay, sir.
Okay. So when I talk about delta S of universe, I'll just take system is 0. So I'll talk about the surrounding, and surrounding is Q by T or W by T. Okay. Moving on. Now let us last slide was adiabatic. Sorry, isothermal. Now let us talk about adiabatic. Okay. So we'll refer to the Joule's experiment, which we did for the first law. Okay. So what is happening here is, let us say that this block is getting dropped and it is hitting. Let me get a pen. Okay. So this block is getting dropped. So basically it is doing pedal. This is pedal wheel work. It is doing work on the system, which is insulated from all the sides. So now see, last slide system was not insulated. It is losing heat to the ambient air. Now the system is insulated. So the temperature will change from Ti to Tf. Okay, let us say this is the initial temperature. Finally, it is heated up to Tf. That work is getting converted to heat. Right? Now, since the system is insulated, so there is no heat exchange with the surrounding, and delta S of surrounding is 0. For the system, how it will be? Okay, now we'll see that it varies continuously from Ti to Tf. So to calculate delta S, I need to integrate dq by T from I to F. Okay, from initial point to final point. Is this clear to everyone? How we are integrating?
Yes, sir.
Okay. Now this dq will be, let us say that this is a constant pressure process. dq could be Cp dt. This will be Cp log Ef by Ti. This is the delta S of the system. Now for the universe, again I will consider both system and surrounding. Surrounding, we have already seen that surrounding is 0. So delta S of universe will be delta S of the system, which is Cp log of this. Is this clear for adiabatic dissipation?
Sir, why delta S of surrounding is 0?
Because we are not doing any heat exchange with the surrounding. Okay, suppose it was losing some heat, then we'll account for that. The same thing what we did in the last slide. System was constantly losing Q, so we said that surrounding entropy is changing while system is not changing. Now this is the reverse case. Here, surrounding nothing is changing, but system is changing.
Okay, sir.
Okay. Okay, moving on. So let us talk about entropy generation in a closed system. Okay. So we have seen that for any process, ds is more than dq by t. Now we have also seen this. Now I want to write equal here. I don't want to write greater than or equal to. I want to write equal here. What I need to account for this. This actually did not do animation, but basically I can say that delta S is equal to delta S by reversible processes plus S generated. Okay, so entropy is generated for any process which is not reversible. Okay, entropy is not a conserved quantity. So it is not a conservation equation, it is a balance equation. So for any closed system, I can say that the delta S is equal to delta S by in reversible process, which is dq by t plus Sgen. And this Sgen is the entropy that is generated. For a reversible process, it will be 0. For any irreversible process, it will be more than 0. Is this clear? What we're talking about in this slide? Any questions? Okay, fine. Then we'll go to the next slide. Okay, so we'll talk about entropy generation in an open system. Okay, so this was for closed system. Let us say I have a piston cylinder arrangement. Okay, I give some heat, and for that we can calculate entropy. So if it is isentropic process, entropy is constant. There will be no. Okay, let me not confuse you. So this, I think everyone is clear. Now let us talk about open systems. So open system, we can assume a general this type of open system where we have some mass in this. This is the control volume. So we have some mass and some entropy in the control volume. This is again intensive property. This is specific entropy, small s. Finite capital S, it will become. It will take care of mass. Now let us say m dot 1 is entering with some entropy. M dot 2 is leaving with some entropy. Some heat is getting transferred to the system and some work is also being done. Now the interesting part is that work is being done, but this will not change entropy. Okay, that we mentioned in the last slide. Now for first law, this is how we used to write energy balance for an open system. Right, we'll take sum of energy of the inlet and outlet. Similarly, we'll do it for entropy. So we'll say that entropy, now entropy we don't write equal to, we write more than equal to this. So again we'll write entropy of a control volume. How it changes with time will be equal, more than equal to the rate of entropy flow from the inlet, the rate of minus the rate of entropy flow at the exit or outlet plus heat supplied by T. Okay. Or I can write, instead of capital S, I can write m into small s. Capital S, again I am writing in m into small s, and outlet is this plus qt. Is this clear?
Yes, sir.
Yes, sir.
Now, again I want to remove this greater than sign. I can write entropy generated. So I can say that this minus this is equal to entropy generated. Someone please mute. So is this clear how we got from here to here? This is the equation we have derived. Now I will say that instead of greater than equal to, I want to write equal to. So I'll write this equal to this. Okay, d of dt of mcv is equal to this term plus Sgen. Okay, what is the entropy that is generated? Now this Sgen will be this minus this. So LHS minus RHS will be how much entropy is generated for that process. So this is what basically accounts for your irreversibility in that process. If the process is reversible, this will be 0. If it is irreversible, it will be more than 0. Is this
सर पर
clear?
एनर्जी बैलेंस में तो QCV और WX टर्म्स भी आती हैं.
Yes. So QCV is here. I could have written CV here. So this is your QCV, right? I have missed this. Is correct? Fine. QCV is here. Now what about WCV? Will I count that in entropy balance? Or why not? I just now told you that work will not change entropy. That is the advantage about having work. It will not have any impact on entropy of the system or surrounding. Only heat will impact on entropy. So that's why we don't have any W term here. Are you clear now?
Yes, sir.
Only
Yes,
mistake
sir.
I've done is I should write QCV here, or I will just say Q here. That will solve your question. So now this becomes correct. Fine. Okay, let us try to wind this up. So TS plot we have already seen. So as we took PDV, that gives us work in that area under the curve, give you the work done for that process. Similarly, area under the TDS plot gives you dQ. What is the heat supplied? And this should be equal based on the first law. Whatever the heat supplied will be equal to work done. Okay? Heat transfer is area under the TS plot. Now let us talk about entropy and disorder. Okay. So second law says that the entropy of the universe is increasing unless everything comes under equilibrium, or you read about astronomical predictions from Stephen Hawking. Otherwise, for normal scenarios, what we talk about in this subject, entropy of the universe is increasing. Now, entropy can be understood to be the degree of molecular disorder. Okay, entropy is the degree of randomness. Molecules are arranged differently, so that is something which we quantify using entropy. Okay, and we can say that adding heat dq by t to the system increases the molecular disorder. It increases the entropy. Okay, so Boltzmann defined entropy by attaching each state with a probability. Okay, so for example, let us say we have a gas, some 4 molecules are there. These are arranged in this pattern. So this has some probability. Now for any other state, molecules are arranged in some other pattern. So that he called macro state. So you imagine you take all the molecules and then you make different arrangement for that. Okay, and then you consider all that, and let us say that is n. N is the number of macro states that are possible. Okay, so if you calculate that, then you will have entropy defined in this way. S is equal to K log N, where K is the Boltzmann constant, N is the number of micro states which are possible for a particular system, and S is your entropy. Is this clear?
Sir, how absolute entropy is being defined here? Will this be equal to that Q divided by T, where
Yes.
Q?
So the idea is that it should be equal to the Q. It should be equal to dQ by T. Okay. And see, this is this is beyond your syllabus, but this is a very abstract concept. He said that there's some probability associated with each of the system, and if you talk about all the possible states or all the possible arrangement of molecules or atoms, that will lead to n. And for that, he has given a constant. This is Boltzmann's constant, Kb. Okay, so let us, I think we'll stop here for today. We'll talk more, we'll take some more examples which will make you clear. Okay, so let's stop for today. This will continue in the tomorrow also we have a class, right? So tomorrow